Problems that I have chosen were dictated by one of the students, and each of them has a small amount of twist which requires a little bit of exercise of the gray cells. The first problem that I take is 414. This is relatively simple. The problem states that the magnitude response of a digital filter with real coefficient transfer function h of z, the magnitude response is shown in this figure, 0 to pi and mod h of e to the j omega. The response is not to scale, 0.2 pi and 0.3 pi. Plot the magnitude response of h of z to the power 4. This is relatively simple. This is what is wanted, magnitude response of h of z to the power 4 required. This is the problem. The solution is very simple. Z to the 4 means you will have e to the power j 4 omega, and therefore this pi shall be reduced to pi by 4. 4 omega equal to pi shall mean omega equal to pi by 4, and each of these shall be divided by 4, and there shall be 4 such sections between 0 and pi which shall repeat this. In this repetition you have to be a little bit careful. You have to extend it. If you want to do that carefully without any mistake, you have to extend this axis to 4 pi. So the division by pi reduces the scale to 0 to pi, and between pi and 2 pi the same thing will be repeated but in a flipped fashion, okay? And therefore the final diagram shall be like this: pi by 4, pi by 2, 3 pi by 4 and pi. This is omega, magnitude of h of e to the j 4 omega. And so we shall have again not to scale like this, and here it shall be in a flipped manner, so it will come like this and this. Similarly here and here between 3 pi by 4 and pi, and these ordinates shall be 0.2 pi by 4, 0.3 pi by 4, this would be 1.8 pi by 4, 0.2 pi, so, and this shall be 1.7 pi by 4. Similarly this would be 2.2 pi by 4, 2 pi plus 0.2 pi, and this would be 2.3 pi by 4, this would be 3.7 pi by 4, agreed, and this would be 3.8 pi by 4. That's it, that's the picture. It shall be repeated, and obviously this is a case of interpolation. It's a case of interpolation, that is 3 samples are put in between 2 successive samples, and this is what the spectrum becomes. And if you want to retain the only one part of the spectrum, then you shall have to use a low pass filter which shall cut out all this, otherwise these will create problems. So an interpolator is always succeeded by a low pass filter, otherwise aliasing may occur, shall occur, yes. The next problem is 442. It is also not difficult. It is given, two magnitude responses are given, GL e to the j omega magnitude and GH e to the j omega versus omega 0 to pi, 0 to pi, and one is a low pass filter and the other is a high pass filter, and the edge is pi by 2. They are ideal filters and therefore they rise like this, 1 drops to 0 at pi by 2, then pi by 2 to pi. All that you have to do is exercise a little care in drawing this diagram. This is what is given, and then you are given a block diagram. X of z feeds into two filters, GL of z squared and GH of z squared. It's a continuation of the previous problem. Here there shall be 2 repetitions e to the j 2 omega, and then this breaks up into 2 channels, GL of z and GH of z. This is y0 of z, this is y1 of z. Similarly, this breaks up. Now the importance of the arrows, the signal flow must be indicated. This breaks up into 2, again GL of z and GH of z. This is y2 of z, y3 of z. The problem is to find out first the transfer functions hk of z equal to yk of z divided by x of z, and then plot their magnitude responses.
Is going beyond pi in the figure in the book.
It does not help us.
Omega is going
At pi, sir, it will continue, it will not fall to zero.
correct. Now this was intentional. Tell me why I did this. Why should it continue beyond pi? It is high pass, and if I continue beyond pi, then it should continue pi 2 and it should 3 pi by 2. That is correct. That is correct. This is a interesting point. We normally do not have to account for this because it's a z squared. It's an interpolator, and therefore you require the sketch between 0 to 2 pi. Agreed? Then only we shall be able to compress it to 0 to pi, and therefore it is important that this continuation is noted. Okay? Very good. Now the transfer functions are of course very simple. H0 would be GL z squared multiplied by GL of z. Then H1 should be GL g squared multiplied by GH, and so on. This is obvious. The plots of e to the j2 omega. Okay, and you shall have to go up to pi. So this is pi by 2, and obviously the the compression will give rise to a transfer function magnitude which is 1 up to pi by 4. That's it. And then from 3 pi by 4 to pi by pi. Okay, so it would be something like this. We don't have to go beyond. We shall cut it off here. We don't require the rest of it. Okay, because pi is our ultimate frequency, digital frequency. Similarly, what would be GH? GH of e to the j2 omega magnitude shall start from pi by 4 and go up to 3 pi by 4. That's right. Once this is known, then only the multiplication of this by the given responses, and you can find out what shall remain. For example,
So in low pass implementation, should it be from pi by 2 to 3 pi by 4, sir? The pass width?
which one? Here?
Yes, sir.
No. What did we have? We had 0 to pi by 2. Okay. So 0 to pi by 4. And then I shall have from 3 pi by 2 to 2 pi, and this becomes 3 pi by 4 to pi, and that's what it becomes, 3 pi by 4 to pi. Okay. So it's a multiplication now of the corresponding responses. For example, I'll simply draw without explanation. It's obvious what it should be. H0, for example, shall be the multiplication of this response by this response. So we shall have only one between 0 and pi by 4. The rest shall be 0. This is pi. H1 of e to the j omega magnitude shall exist. H1 is this low pass thing multiplied by the high pass response, this one. So I shall get from pi by 4, 3 pi by 4 to pi. That's it. Three pi by 4 to pi.
So here we should end it to 0 or no?
Our processing cannot go beyond this, cannot go beyond pi, and therefore we shall bring it to 0, okay? Or we shall leave it there, it does not matter. We shall never reach pi, okay? Then H2 and H3 both shall be band pass. Okay. H3 shall extend from pi by 4 to pi by 2. This is H3. I am not drawing the diagram. And H4 shall extend from pi by 2 to 3 pi by 4. That's right. So that solves the problem. Next we enter a domain which requires programming. 474. You cannot do it by observation. In 474, 5 transfer functions are given, H1, H2, H3, H4 and H5. I am not writing them down. And it says determine the 0 locations of each. Obviously you cannot do it analytically. The degree, the order is 6. You have to use a MATLAB program or a root finding program to determine the roots, and then answer the following question: does any of them have linear phase? Well, that can be answered. If it is linear phase, then the coefficient should be symmetrical or anti-symmetrical, and only one of them, the second transfer function H2 of z, if you notice carefully, has symmetrical coefficients, and therefore that is linear phase. From the others, which one is minimum phase and which one is maximum phase cannot be answered without finding the roots. But there is a way which I have not discussed in the class. We shall look at this in a later problem. Later problem is also like this. I have tried to break into this and find the solution. That might answer this question also, but may not also. Okay, we shall have to live with a may. Why? We will come back later. So H2 is minimum phase, not minimum phase, a linear phase. Linear phase, that is definite. There is no question mark here. But whenever you are answering maximum phase or minimum phase, there is an ambiguity. There may occur an ambiguity.
What is the significance of the first part, sir? They have the same magnitude of the DTFT is the same. So one condition is given that all the 5 sequences are same DFT. Magnitude.
No, this is not info. That is the problem I will take later. 76, I will take later. But let us do the in between one, 475, which happens to be easy. 475, we shall take 476 also. In 475, the statement of the problem is a third order FIR filter has a transfer function G1 of Z is equal to 6 minus Z inverse minus 12 Z to the minus 2 multiplied by 2 plus 5 Z inverse. This is the transfer function that is given. Then you have to answer the following questions. Determine the transfer functions of all other FIR filters which have the same magnitude response as that of G1 of Z. So find all transfer functions whose magnitude is the same as the magnitude of G of e to the j omega. Okay. Second part, which ones are minimum phase and which ones are maximum phase, and which ones are maximum phase. And the third part, part C, relates to the impulse response and partial energy. This is where the answer to the question of minimum phase and maximum phase lies, and I shall point it out when I talk about 476. And this third part is simply a matter of computation. Once you find out the impulse responses of all these transfer functions, if you can find out the transfer functions, you know the impulse response, right? The coefficients of the variable. These are the impulse response coefficients. So let us first find out all transfer functions whose magnitude is the same as that of G of e to the j omega. Now since it is only a third order, there has to be a real pole, and the real pole is already given. 1 plus 5 by 2 Z inverse. This is the real 0, not pole. This is the real 0. 0 is at minus 5 by 2, minus 2.5. Okay. And then the other quantity 6 minus Z inverse minus 12 Z to the minus 2. A little bit of thought will show that you can factorize this into 6 multiplied by 1 plus Z inverse, 1 minus 2 Z inverse. Okay. The clue was very simple. So if you put here 6 plus 6 Z inverse, then you get minus 12 Z inverse minus 12 Z to the minus 2. So 1 plus. No? Have I made a mistake? 6 minus 12, yes, 1 minus 2 Z. 6 minus 12, then
6 minus 9 plus 8.
Yes, sir.
oh, I made a wrong factorization.
The roots will be minus 4 by 3 and 3 by 2.
Okay, let us see. 6 minus Z inverse minus 12 Z to the minus 2. What is the factor? 6 minus 9 Z inverse plus 8 Z inverse minus 12 Z to the minus 2. So this becomes 3, 2 minus 3 Z inverse plus 4 Z inverse 2 minus 3 Z inverse. I stand corrected. 2 minus 3 Z inverse. This is not correct. So I get this as equal to 3 plus 4 Z inverse 2 minus 3 Z inverse, and I can write this as, in order to make the zeros transparent, I write this as 6 1 plus 4 by 3 Z inverse and then 1 minus 3 by 2 Z inverse. So my given transfer function G1 of Z is equal to 12. 12 is okay? 1 plus 5 by 2 Z inverse, then 1 plus 4 by 3 Z inverse, 1 minus 3 by 2 Z inverse. Before I find the alternative transfer functions, notice that this is maximum phase. All zeros are outside the unit circle, okay? And then what your procedure would be to replace each of these factors by another factor such that the magnitude is the same, not 0. First magnitude should be the same. Now the magnitude of 1 plus 5 by 2 Z inverse, 5 by 2 plus Z inverse, the magnitude of this for Z equal to e to the j omega, it is all pass, and therefore this is 1. This is the clue to the whole solution. And therefore if you write G2Z as equal to 5 by 2 plus Z inverse multiplied by 12, then 1 plus 4 by 3 Z inverse, 1 minus 3 by 2 Z inverse, you do not change any other, the magnitude shall be the same. But then you have to bring this 5 by 2 out, so it would be 30, 1 plus 2 by 5 Z inverse multiplied by these two factors. This will have the same magnitude response, and this is what you have to repeat for the other two factors taken one at a time. So how many do you get? We have a G1, then G2, G3, G4, then taken 2 at a time, so G5, G6, then taken 3 at a time, G7. Is that all?
Yes.
7 transfer functions, and the last one shall be minimum phase. In between you shall have mixed phase transfer functions. Okay? So the third part, as I said, takes care of partial energies. That is, third part asks for finding GKN and then calculating EKN as, what is the 8?
Sir, when we will take 2 at a time, we can make 3.
From 3C2 is 3. You are right, you are right. One more, yes. That is right, that is right. I made a mistake. The third one says GK squared M, M equal to 0 to N, 0 less than equal to N less than equal to 3. You see, GK is an FIR. It is FIR, finite impulse response. And if you find EK0, it only contains GK0. So it is partial energy. Then when you make N equal to 1, it is again partial energy, it will be increased. The total energy shall be M equal to 0 to whatever the highest length is. What is the highest coefficient? GKs, what will be the length of the GKs? All of them are third order, and therefore the length would be 4. Isn't that right? He wants only to you to calculate from 0 to 3, in other words not the total energy but the partial energy, and then some identities or inequalities have to be shown. This is a matter of computation, you can do that. But this this example, it is still, oh, n is equal to 3 is the total energy, yes, you are right, because m equal to 0 to 3 it is the total energy. Okay, so Ekn, n equal to 0, 1, 2, 3, with 3 it is the total energy. Now partial energies obviously shall be smaller than the total energy, because there is a square here and this is a real quantity, so it's whether positive or negative, it shall add up as you add up more samples. The partial energy it is a property of minimum phase and maximum phase functions that the partial energy is higher for minimum phase and lower for maximum phase. In fact, if you take all the transfer functions and calculate the the partial energies for all, then the partial energy for the minimum phase shall be the highest of all of them. You have 8 transfer functions, you say. Of these 8, the 8th one, the minimum phase one, shall be the highest partial energy. Whether n equal to 0 or 1 or 2, it is always true. And the maximum phase one shall have the minimum partial energy. Okay? And many a times looking at the constant term suffices. The one with the highest constant term is a candidate for minimum phase, but you cannot say definitely, because the interior ones may also contribute.
Vice versa is not true.
No, no. It's only a candidate. It is a candidate for minimum phase, but you cannot say definitely. Now we take 476, and the question, I xeroxed it, I didn't want to write all of them. Is it clear on the Z transforms of 5 sequences of length 7 are given below. Okay. H1, H2, H3. Magnitude of the DFT for each of the above sequences is the same. Which one of the above Z transform has all its zeros outside the unit circle? Okay. Now outside the unit circle, all its zeros outside the unit circle means that the product of the roots shall be greater than 1. Agreed? Therefore, the coefficient of z to the minus 6 shall be greater than 1, and only H1 and H3 qualify, right? Is that clear?
It is not necessary condition.
It is,
Suppose we have 1.8 force. Product is the same.
if all the roots are outside the unit circle, then Zi greater than 1, I equal to 1 to 6.
It's okay, but it
Pardon me?
possible that one of the pole is one of the zeros inside the circle.
No, no. The question is, which one of the above has all its zeros outside the unit circle?
So it's not the same as the.
Yes, sir, it is not necessary.
So
Wait,
still the
wait,
product can be-
Still the product can be?
8 into 4.
If some of the zeros lies inside and some of the zeros
No, your question is, which one of the above Z transform has all its zeros, all,
Yes,
Yes, sir.
that's why now we are saying.
all its zeros outside the unit circle?
Because you cannot say that if 3 point.
If say we have a 0,
No, no,
8 and 4.
this is okay. That's why I am saying they are candidates. It's not necessarily, we cannot pinpoint, we cannot answer this question without actually finding out their roots. We can only say which are the candidates, possible candidates. Possible candidates are H1 and H3. They are candidates for maximum phase function. Okay. Of these two now, of these candidates, they may or may not. No, that their maximum.
So minimum phase.
Pardon me?
It's for minimum phase.
Zeros outside the unit circle is minimum phase, maximum phase. They are candidates, but of all these, you cannot say, okay, none of the others qualify for this. None of the others, H1 and H3 are the only ones. The more probable one, which one is more probable? Maximum phase has to have minimum partial energy. Maximum phase has minimum partial energy. Now obviously if you look at H1 and H3 and if you calculate the partial energies, it turns out that H3, why H3? Well, H3, no one can't say definitely. Minimum constant term is not minimum here. No one cannot say definitely. You have to calculate the partial energies to be able to find that. But calculating partial energies for all of them is as good or as bad a task as finding out the actual roots, and therefore one cannot answer definitely. Which one has all its zeros inside the unit circle? Now who are the candidates? Inside the unit circle, all its zeros inside the unit circle means the constant term must be less than 1. Not constant term, the highest power, that is coefficient of z to the minus 6. Now which one has the all others? H2, H4 and H6, and of all these, which one is the lowest? H2, but one cannot say
So
definitely.
in case H5 will be the minimum phase, but H5 is a mixed phase. We know that because the alpha it's a
Because
linear phase function H5.
so H5 goes out of the picture. Yes, very good observation. 0.75, 0.75. So H5 is neither minimum phase nor maximum
Well,
phase.
according to our assumption that the Z is to minus 6 coefficients.
Yes.
Less than 1. So it can be candidate means
No, it's a mixed phase. It cannot be a candidate for minimum phase or maximum phase. No, that candidacy is barred. All right. So it goes out of the picture with respect to these two questions, right? So you have to choose between, you're narrowing down your vision. But even then, even if you pinpoint on one, you cannot say definitely without finding the roots. Therefore, this solution of this problem requires finding the roots to be able to arrive at a definite answer. Partial energy is an indication, but not a confirmatory test. All right?
So what is the significance of first statement? The magnitude of the DFT of each of the following sequences is same.
You not use the last statement.
Okay. Because the last part of the question, how many other real sequences of length 7 exist having the same DFT magnitude as those given above? DFT magnitude means magnitudes of x of k, and this number has also to be determined by actual calculation. It turns out to be 26 or 27. That is also a guesswork. You have to actually, this question cannot be answered without using MATLAB. All right?
Sir, but if there is any significance of the first statement, sir,
Which statement?
so the magnitude of the DFT of each of the above sequences is the same.
This is relevant to the last one.
It has nothing to do with
No,
finding the
no, no.
Well, then the energy will be same.
Energy will be the same. Energy will be the same, but that does not mean
So
DFT, you see, energy is magnitude xk squared summation over k. That does not mean that the sequences are identical. No, there may exist many other sequences, and you might get tired in finding out how many sequences have the same DFT. Pardon me? If we add up H1 and H2,
so they become, and that becomes linear phase. Does that infer anything?
the sum of two linear phases is not linear phase.
No, sir. H1 plus H2 is the linear phase.
Correct. That does not indicate anything. We can have, in other words, we can decompose a linear phase into sum of two polynomials. One can be maximum phase, one can be minimum phase, both can be mixed phase. It doesn't matter. It doesn't indicate anything. The product of two linear phase polynomials is linear phase. Okay? That's ensured. Product of two linear phase polynomials is linear phase. Our next problem is 482. 482 states, let f1z denote one of the factors of a linear phase FIR transfer function h of z. H of z is f1z multiplied by some other factors, let us say f2z. This is given. And the question is, determine at least another factor f2z of hz for the following choices of f1. The choices are A, f1z equal to 1 plus 2z inverse plus 3z to the minus 2, B, f1z equal to 3 plus 5z inverse minus 4z to the minus 2 minus 2z to the minus 3. One of the approaches can be find out the roots. For a quadratic it is perfectly all right, we can find the roots. For a cubic we have to search for the real root, then find the roots of the quadratic. But there is a simpler approach. Simpler approach is, again obsession with all pass functions. In all pass functions, the poles and zeros are reciprocal pairs. Agreed? Reciprocal pairs. And the magnitude of the numerator is the same as the magnitude of the denominator. Agreed? In an all pass function. The second important fact is that for a linear phase, zeros occur in reciprocal pairs. That is, if z0 is a 0, then 1 by z0 is also a 0. Now, if I want to make an all pass function out of this, 1 plus 2z inverse plus 3z to the minus 2, do not worry about stability. If I want to make, then my function obviously shall be 3 plus 2z inverse plus z to the minus 2. Now, if this is d of z, then obviously this is z to the minus 2 d of z inverse. In other words, if z0 is a 0 of dz, then 1 by z0 is a 0 of the numerator. And therefore, my clear choices, obvious choices would be f2z is 3 plus 2z inverse plus z to the minus 2. Just reverse the coefficients. For A, and for B it shall be minus 2 minus 4z inverse plus 5z to the minus 2 plus 3z to the minus 3. That is it. Very simple question. Two facts I have used. One is that the numerator of an all pass function can be written as z to the minus n d of z inverse. So the zeros and poles are in reciprocal pairs. and for a linear phase function the zeros occur in reciprocal pairs. So, the only other term that I have to add is this. Okay. I can add more terms. He says at least one factor. Okay. Let me complicate the problem a little bit. Suppose I have h of z, I have obtained this 1 plus 2 z inverse plus 3 z to the minus 2 multiplied by 3 plus 2 z inverse plus z to the minus 2. Suppose the question is to find a fifth order linear phase polynomial by using the simplest possible modification h prime of z, simplest possible modification. What shall we do? Multiply by oh wonderful, multiply by z inverse. Yes, that will become a fifth order. Is it linear phase? Yes, it is linear phase. Okay. Suppose we want to change the now wait a second, suppose that is not permitted. What is the next simple? Plus minus 1. So, we shall use 1 plus minus z inverse. If I use a plus sign, shall it be symmetrical or antisymmetrical? If I use the plus sign, the impulse response shall be symmetrical. Okay. If I use the minus sign, it becomes antisymmetrical, right? One more complication. Suppose this is given. You want to make the transfer function symmetrical impulse response. This is given. You have to add one or more terms. The degree is no restriction, so that you get a symmetrical impulse response. Yes? How would you do that? Just square it. Then this anti shall go. If you square it, then this becomes a symmetrical impulse response. So, symmetrical multiplied by symmetrical shall also remain symmetrical. On the other hand, if this is given and you want to make it asymmetrical, then you raise to the power 3. So, 1 minus z inverse raised to even powers gives you symmetrical impulse response. Odd powers it gives rise to antisymmetrical. If on the other hand I had this one and I raise 1 plus z inverse to any power, even or odd, does the symmetry or antisymmetry change? No, it does not change. Okay? Right. These are some of the interesting points. Okay. The next problem is 485. It's an interesting problem. 485, let me see. Shall we do this or shall we? Okay. We may conclude with this. 485A, show that the phase delay tau p of omega. You remember we had defined group delay tau g of omega as the negative gradient of phase minus d phi omega d omega. This is what is significant for a linear phase and any group of frequencies, transmission of any group of frequencies. But phase delay tau p omega, which is defined as minus theta omega over omega, is also important in some cases, minus theta omega divided by omega, particularly when you are not concerned with a band of frequencies. For a single sinusoid, this is okay. Phase delay is okay. Whenever there is a group of frequencies, the modulation is involved, that group delay is the more important thing. This problem says tau p omega show that the phase delay of the first order all pass function A1z equal to d1 plus z inverse 1 plus d1 z inverse is given by tau p omega approximately equal to 1 minus d1 divided by 1 plus d1 equal to delta, defined as delta. This is the first part. And the second part says design a first order all pass filter given that delta is 0.5, tau p omega is 0.5. See, tau p omega normally should be a function of frequency. It is approximated by a constant. The constant is 0.5 for a given design, and the sampling frequency Fs is given as 20 kilohertz. You will see the relevance of this. Fs is 20 kilohertz, then determine the error in samples, error at 1 kilohertz in the phase delay from its design value of 0.5 samples. Okay? The sampling frequency is 20 kilohertz. Error, you have to find the error, that is deviation from 0.5 at 1 kilohertz. Why is the sampling frequency given? So that you can find the normalized digital frequency, small omega. All right. Now let us do the first part. Second part would be very simple. You can write A1 of e to the j omega as equal to d1 plus e to the minus j omega divided by 1 plus d1 e to the minus j omega. In finding the phase, it is convenient. This is a crucial manipulation, simple but very crucial. It is convenient to write this as e to the minus j omega, write the numerator and denominator in the same form except the sign of the exponential. So I get 1 plus d1 e to the j omega, 1 plus d1 e to the minus j omega, and therefore the phase is given by minus omega for this factor, plus for the numerator it would be tan inverse, yes, d1 sin omega divided by 1 plus d1 cos omega, and for the denominator it shall be tan inverse minus d1, and therefore it would be twice. When you bring it to the numerator, the sign is changed, so it is twice. All right, and therefore tau sub p of omega, this is a trick that we always exercise in the case of all pass functions. We take out the linear phase term first and then we write the tan inverse function. It becomes twice of that. So tau p omega is minus 1, you divide by omega, 2 by omega tan inverse d1 sin omega divided by 1 plus d1 cosine omega. When omega is small, when theta is small, tan inverse theta is approximately equal to theta. Tan inverse theta is approximately equal to theta. Sin inverse theta is also approximately theta in radians, that you must remember. Okay, therefore tau sub p of omega, obviously if I have to make it independent of omega, I must make this approximation, approximately equal to minus 1 plus 2 by omega. Instead of tan inverse, I write the function itself, 1 plus d1 cosine omega. And you see, when omega is small, sin omega is approximately omega. Therefore, minus 1 plus 2 by omega d1 omega, and cosine omega is approximately 1. When omega is small, cosine omega is approximately 1. And now it becomes independent of omega, and you can you can verify that this is 1 minus d1 divided by 1 plus d1, which has been defined as delta.
So why are you assuming omega is small?
Oh, I have to assume omega small to be able to convert it into a function independent of omega. All right. In other words, this tau p omega will be exact when omega equal to 0. So tau sub p of 0 shall be exactly equal to delta. When I increase omega, it shall, there will be error. I don't know whether the error will be positive or negative. Okay. So the second part, in the second part, my time is over. Delta equal to 0.5 gives rise to d1 equal to 1/3, and 1 kilohertz is equivalent to omega equal to, yes, 1 kilohertz is 2 pi radians per second, and omega is 2 pi f divided by fs, and therefore I shall get 2 pi divided by 20, that is pi by 10, and then you have to calculate tau p at pi by 10, and my calculation comes out as 0.503. So it's not much of a deviation. 20 kilohertz sampling, 1/20th of that. 20 kilohertz sampling means I can go from 0 to 10 kilohertz only, and even at 1 kilohertz the deviation is only 0.003. Okay.